don't automatically go to the back, don't block people. Okay, come, first one. What is the answer for the first one? Energy. Energy is the capacity to do work. This is our definition. We need to memorize it. And then I also told you principle of conservation of energy. You must memorize it also. Most likely it will be tested out. Energy cannot be created, cannot be destroyed. Total energy remains the same. Okay, it's a constant. What else is there for our principle of conservation of energy? It can only be converted from one form to the other. Okay? Now, we have an iron ball released from a height above the ground, assuming air resistance is absent. So no losses. Let's consider the GPE and the KE and the total energy. Now, before we start on this table, what can you tell me about the total energy in the system? Tasha, what do you think? What is the total energy in the system? Two options. Constant, not constant. Constant. Yeah. Why is it constant? Because of our principle of conservation of energy. Okay? Total energy remains the same. So can we fill in this column already? And right. Over here we have 12. On our last column, it is all 12. So since this is 12, the first row, what will the kinetic energy be? 0 lor. Okay, 0, see, all here, all 12. So just simple addition and subtraction. Make sure all of them add up to be 12. So check your answers. It's correct. Put a tick. Then what do you notice about the potential energy as the height decreases? The gravitational potential energy will also decrease because it is a function of the height above the ground. The smaller the height above the ground, the lower the gravitational potential energy. So as it drops, what happens to its speed? It increases. That is why our kinetic energy increases. Hurry. Do you do your work or not? Huh? No. Then why are you sitting now? So that I can be reminded that you didn't do your work. Okay, what forms of potential energy, kinetic energy does the ball have before it is released? So what does it have before it is released? Anqi, what does it have? Only? Only? Yes, she is correct. There is only gravitational potential energy. Please spell it out. Do not write KE only. What happens to the potential energy and kinetic energy as it is falling to the ground? So we need to consider two different types of energy. As it is falling, what happens to the potential energy, Moaz? Okay, good. Potential energy decreases, kinetic energy increases. Okay, now when it is 0.75 meters above the ground, what type of energy does it have? Yes, both are. Yes, gravitational potential and kinetic. These combined, they are called your mechanical energy. Right? Remember, your potential energy and kinetic energy, they are all mechanical energy. What forms does it have? At the instant it hits the ground. When it hits the ground, what is the height above the ground? 0. So the speed must be the greatest. So it will have only kinetic energy. Now it can be confusing to you because of the way we phrase it. The instant it hits the ground, what do you think is the speed? You are tempted to say the speed is 0, right? Because if you like pause it there, the speed should be 0 lah. But if the speed is 0, then the kinetic energy also 0, right? If the kinetic energy is 0, gravitational potential energy is 0, then where is all the energy? Is the total energy 0? Cannot be. Your principle of conservation of energy states that energy cannot be created, it cannot be destroyed, it cannot be converted from one form to the other. We know that the the height above the ground, when it hits the ground, is 0. So no more gravitational potential energy. Therefore, all of the energy is converted to kinetic energy. Okay? So, we need to understand that the moment it hits the ground, speed is maximum. Okay? That's why kinetic energy is maximum. You compare that to throwing a ball upwards. The ball goes up and up and up. When it reaches the highest point, what happens to the speed? What happens to the speed of the ball when it reaches the highest point, when you throw it up? 0. Okay, this is the difference between the ball being thrown upwards. When it reaches the maximum height, speed is 0. Kinetic energy is 0. Gravitational potential energy is highest. Versus, you drop the ball. Drop, hit the floor. Kinetic energy is highest. Gravitational potential energy is lowest. Alright? Okay, so what do you notice about total energy? It has to be constant. So now, find the mass of the ball. Taking gravitational field strength with 10 newtons per kilogram. Which formula do you think is useful for us? You have two options, half mv square and mgh. Which one do you want to use? Okay, I think mgh is a more sensible option because if you want to compare the kinetic energy, you can. But did they tell you the speed? No, they didn't. So you don't know the speed, you don't know the mass, you can't find out the answer. Okay? Whereas if you use your gravitational potential energy, we can just use mgh. Okay, 12 joules. That is our gravitational potential energy is equals to mgh. This is at 1 meter in height. That is the highest point. There is no kinetic energy involved. So all of the energy is just gravitational potential energy. So we rearrange this. We divide by G. We divide by H to get mass, which is 1.2 kilograms. Always start off with a formula for physics. Any questions? Okay, now pendulum. For position A, when it is at position A, which is the highest point, what can you tell me about the speed? Hurry. Speed is 0. Okay, what about the kinetic energy? So what about the total energy? 20 what? Millijoules. Okay, sit down, hurry. So we can see that total energy again will be constant, 20 millijoules, because of the principle of conservation of energy, and we assume that there are no losses due to friction, air resistance, so on and so forth. So based on all these, similar to the previous page, we are able to fill in all the other blanks. Just make sure they all add up to be 20 millijoules. Yes. Everything correct? Everything correct? So at which position does the bob have the greatest speed? Yes. When does it have the greatest speed? Point C. Okay. Huh? They say that C is the lowest position. So D is slightly higher lah. Okay, but from the diagram, they look almost the same. But so we have to read the question carefully. Otherwise, I'm also quite tempted to say D also lah. But it's not, okay? At what position does it have zero speed? Harif already gave us the answer. A, the other one will be the other extreme end, which is E. And then compare the speeds at B and D. Well, which position does it have a greater speed? So how do we do this? How do we compare the speed between B and D when they don't give you the speed? Yeah, we look at the kinetic energy. Just by looking at the kinetic energy, which is half mv square, where we are comparing the kinetic energy, we are just comparing the different speeds. Higher the kinetic energy, higher the speed. So at which one does it have higher kinetic energy, B or D? So let's look at the table. D. D has higher kinetic energy, so our answer must be D. Okay? So now we shall go on to the rest of our slides. Where did we stop for our last lesson? Have we covered this? Okay. Oh, then I said I wanted to let you all watch the video, right? Let's see if it works, huh?
Oh, you're up. This is good. We're gonna rob a bank. Oh, Lord. Please deliver.
Here's what we're gonna do. I'm fascinated with pendulums, aren't you?
Okay, can somebody help me in the volume? Anybody? Or maybe? Otherwise, we are gonna have to watch this without volume, huh? Okay, it's plugged in already. Also plugged in. Yeah, it looks like it's max to me.
Here's what we're gonna do. I'm
That one is only for the display mount.
No, but soon our slide is best computer than can already.
Is it? Function.
fascinated with pendulums, aren't you?
Okay, never mind. Let's just watch this. I'll explain what's happening. So, in this
Here's what we're gonna do.
demonstration,
I'm fascinated with pendulums,
this guy
aren't you?
is attaching
Very.
I know.
Especially today.
Mom said I was special. All right, so this goes here, and now, watch this. We're gonna be able to swing this.
We are.
Yes.
Oh, good.
So come over here and join me in the
What?
little lab. All
Okay.
right. So, and I wouldn't want you in the way because you are
No.
a precious commodity.
Yes.
So stand right over here.
Okay,
So that's why I
behind
have
the
this marker.
cone.
No, you to the side of the marker. See the marker right here? Okay,
Yeah.
no, right over here.
Yeah.
Okay, good. So here's the law.
Okay.
You can't get out more than what you put in. It's the law of conservation.
Right.
Okay. So if I hold it here like this,
Right.
and like I'm swinging a kid, and I push a little energy into it, I probably can come back farther than this. Right. So watch this. Ready? So pretend like this is you. All right. So here we go. It's out here like this, and it comes back, and boom. See how it smacked?
I like that game.
Yes. That's a little game.
Thank you.
So, but notice I put energy into it like a kid. I'm swinging it. I'm not.
Notice his hands. What did he do? Did he drop
So
or
pretend
he
like this
push?
is you. All right, so here we go.
he pushed.
It's out here like this,
he
and
pushed
it comes
it.
back,
That's me.
and
Came back.
that he
boom.
gets
See how
taken
it
out.
smacked?
I like that game.
Yes, that's a little game.
Thank you.
So, but
He's
notice I
going
put
to-
energy into it like a kid. I'm
Right.
swinging it. I'm not letting just gravity do it. So I'm out
Push
like
again.
this, and watch. I'm going to little smack. Here we go, and boom.
So it
See?
Yeah.
Okay, so now that we've
Stands
practiced, now
beyond
it's
the
your
original
turn.
position.
So here's what you're going to do:
Okay,
is
because
that
I
you
exerted
are going. It's going to be
the
okay.
force
You don't
in
have to
the
worry about
beginning.
it.
Yeah.
But I don't want you to be able to move because
So
I don't
he
want you to
gave
get
it
hurt. So that's why I'm going to put your
kinetic
back against this wall.
Give it
Okay.
extra
Now you
kinetic
have to put
energy.
your head against the
Now
wall as
he's
well.
asking this lady to
Good. So
stand
now
on
you
one
can't
side.
move. Got it? Are you okay? So
Yeah.
now watch. I'm going
gonna
to take
put
the
it
bowling
over
ball and bring it back to your
face.
face. Okay. No, put your hand down. It's okay. Okay. So you see how we're right here at your nose?
Yes.
Can you see that? So we are right here just touching your nose.
Yes.
If I let go, according
And
to the
he
laws of
says
motion,
that
Oh my gosh, you
it
scared
should
me there for
come
a
back
second.
and it should not
He's
hit
not
you in
going
the
to push
face.
it. What happens
Okay,
if he
now I
pushes
saw
the
this on
ball
the
away from
internet,
her?
so I think
You'll
it'll be good.
smash her in the
Okay,
face, right?
you ready?
Because you can trust
So he
everything
only
In the
we
does
do on
internet.
the
Okay,
internet.
ready here. I'm
Just
gonna let go.
to-
But what, you have to watch it because it's the freakiest thing in the world. Watch. Here it
He dropped
goes.
it.
Here it goes. It's swinging back. It's a 16-pounder. It's back and. Oh, did you see your little place that was there?
did
Isn't
hit
that
her.
great? Wasn't that
much fun.
super?
Almost hit her, but
Steve.
didn't.
No,
Why is
here's
that
the-
so? Because of the conservation principle of conservation of energy, we cannot create energy out of nowhere. So since he dropped it, that means all the gravitational potential energy was converted to kinetic energy. Then it went to the other side, and then it came back to her. But this time, it went slightly lower. And then when it came back the second time, it came back even lower, right? Further and further from the lady. Why is that so? Yes, energy is lost. Where? Where did the energy go to? Surroundings how? Air resistance, friction. Okay? These are the usual ones that are present. Friction in a pivot. Because it is swinging, so there will be movement, so there will be friction in the pivot. So in this case, he only dropped it. Earlier on, we saw that he pushed it. That means he supplied kinetic energy in addition to the gravitational potential energy. Okay? Okay, so let's go back to our slides. Why didn't it hit? Okay, we cover all this already. So now, when the force is exerted in the beginning, initially from W, okay? Instead of just dropping it, we exert a force. That means we gave it initial kinetic energy. So the total energy at W will be your gravitational potential energy plus the kinetic energy that I provide. And it will swing. It will reach a highest point Z. At this point, is it stationary or is it still moving when it is at the highest point Z? Stationary. So is that kinetic energy? It is stationary at Z. Is that kinetic energy? Don't have. What about at Y when it is at the lowest position? Is there gravitational potential energy? It will be the lowest lah, okay? And the kinetic energy here will be the greatest because it is at the lowest point. So from W to Y, total energy here equals to total energy at Y. Total energy at Y comprises kinetic energy only. So from Y to Z, all the kinetic energy will become gravitational potential energy at Z. Okay? Any questions? So since the gravitational potential energy at Z is larger than that at W, then of course it will go higher. Because GPE equals to mgh. M and G didn't change, so H must change. Okay, so now we have a nail being hammered into a plank, when you raise the hammer, what kind of energy are you giving it? GPE, because you're raising it up, so it has the potential energy to do work. So that's part A. Part B, when it falls, when you drop it, this energy converted into kinetic energy. Then what is this energy used for? Drive the nail into the plank. All logical common sense. What other energy forms are produced? Okay, sound. What else? Heat. Where's the heat from? Because when you hit the hammer on the nail, there will be friction, there will be heat generated. Okay, so sound, thermal energy, kinetic energy. Sound is actually kinetic energy in air molecules. Okay, so in space, when you do not have air molecules, so there is no kinetic energy for the molecules to transmit a sound. That is why we can't hear anything in space. Okay? So what is the difference between ideal and real pendulum? We covered it already. There is energy losses in a real one. Zafan, sit up straight. Okay, so this was mentioned. Your frictional and your resistance type of forces, whether it's your air resistance, your resistance in water, so on and so forth, they are all converted to thermal energy. That this is dissipated to the surroundings, and it cannot be converted back into kinetic or gravitational potential energy, in this case for the pendulum. That's why it will slow down, and eventually it will come to a stop. And the principle of conservation of energy still stands. All the energy is conserved. Okay? So let's look at this case where it is not ideal. This is the original height of the ball. We drop it, the gravitational potential energy becomes kinetic energy. GPE decreases, KE increases. When it hits the floor, what type of energy, what types of energy are present that are lost? We have heat and sound. So in red color. So the total kinetic plus gravitational potential energy is now lower. Okay? So when it rebounces, your kinetic energy becomes your GPE, and you realize that it does not reach the original height. Now, the maximum height at point number 4 is lower than your original height, which is what we observe in our daily lives, where we play basketball, for example. Okay, so likewise for the ideal pendulum, initial GPE at W, we are not pushing it, we are just dropping it, so no kinetic energy at W. When it goes down to point Y, at point Y, there is only kinetic energy. We say that there isn't any gravitational potential energy because it's at the lowest point. And then we also have energy loss due to friction and air resistance. Okay, so the mechanical energy is now reduced. Then from Y to Z, the initial kinetic energy at Y is converted to gravitational potential energy at Z, plus, again, from Y to Z, you still have energy loss due to friction and air resistance. So take note, at point Y, the final KE, because when it drops from W to Y, it is the same kinetic energy from Y to Z. It is the same kinetic energy. Okay? So example, 500 gram ball, it is not in SI unit, so you must remember to change it to kilogram, is thrown vertically downwards. Are we saying that it is dropping? No, it is not dropping. It is thrown vertically downwards from a height of 10 meters with a velocity of 5 meters per second. So we give it, yes? Chai, Farah, Nadia, Winnie Yong. Okay, go for a dental appointment. The other students are not here. They are in IT room 3. 2 levels up. Okay, Winnie Yong, please go with them. Okay, so now we have a ball that is thrown downwards. What type of energy are we supplying it with? Kinetic energy. And at the same time, it also has gravitational potential energy because it's quite high. So it hits the floor and then it bounces, rises to a maximum height of 8 meters. Is this higher or lower than the original? It's lower, it's still lower. So determine the energy loss at the bounce. Okay, so our initial kinetic energy plus initial gravitational potential energy. This must be equal to the final kinetic energy, final gravitational potential energy plus energy lost. This is still our principle of conservation of energy. So now all we need to do is to just substitute in the correct values. Initial KE, so half mv square, where m is the mass of the ball, v will be the velocity, the initial one, plus mgh, where h is the initial height of 10 meters. Okay? When it reaches the top maximum height already, final kinetic energy will be 0 because momentarily it is at rest at the highest point. So kinetic energy is 0 plus mgh2. h2 is the new height, which is 8 meters, plus your energy lost. Substitute in everything, you realize that you have numbers, all of them, and you have one unknown, and we can calculate it to be 16.25 joules. Can follow the logic here? Anybody lost about the logic? Okay, convert it to 3SF. Okay, in physics. That's all that we have for work. So right now, I want you to do your workbook 6B in class. Let me share with somebody first.